Imagine trying to teach an AI, not just to follow instructions, but to actually learn and adapt, like really learn from experience.
Right, moving beyond just solving one static problem.
Exactly. Think less about, say, a single math calculation and more about an AI that gets better at planning your trips over time,
Right.
learning what works.
Mm-hmm. Learning from feedback, seeing what sticks.
That's the really exciting challenge we're diving into today. How do we build these AI agents, especially the ones using large language models, so they can genuinely self-evolve, learn through doing things in dynamic, interactive situations?
Yeah, and what's really at the forefront here is getting past training LLMs for those static single-turn tasks. We know they're good at generating text or code, one
Okay.
input, one output, basically.
Standard stuff now, almost.
Kind of, yeah. But the real jump is creating agents that can handle, multi-turn interactions, conversations, sequences of actions.
Like AI assistants helping with complex projects. Or robots learning tricky movements.
Exactly, or even tutoring systems that adapt as a student learns. These agents need to make sequences of choices. They need to remember what happened before.
And react to feedback that might be totally unpredictable.
Precisely. They have to adjust based on what the environment throws back at them.
Okay, so that leads us straight into the core of today's deep dive. We're looking at some new research outlined in a paper titled Understanding Self-Evolution in LLM Agents via Multi-Turn Reinforcement Learning.
And this comes from a pretty impressive group of researchers, folks from Northwestern, University of Washington, Stanford, Microsoft.
NYU, Singapore Management University, Imperial College London too. A real collaboration.
It is, and what they're tackling here is, well, it's a significant gap in how we understand these agents. The potential for LLMs and interactive roles is obviously huge.
We see the possibilities everywhere.
Right, but the actual science, the fundamentals of how to train them effectively and stably using multi-turn reinforcement learning, that's still pretty new territory.
Reinforcement learning being the trial and error learning across multiple steps.
Exactly. So the big question they're asking is, what really makes these LLM agents learn reliably in these changing environments? What are the key design choices?
And our mission here, for you listening, is to pull out those crucial challenges and the promising new ideas they explored, give you a clear, quick grasp of how we might get AI to learn from its own experiences, kind of like humans do.
So they introduced this new framework, a general way to think about training these interactive agents. They call it StarPO.
StarPO, STARPO. That stands for State Thinking Actions Reward Policy Optimization.
Okay, so digging into StarPO, what's the big shift here? How is it different?
Well, the key thing with StarPO is that it moves the focus. Instead of just optimizing one action at a time.
Like, what's the best next move?
Right. It looks at optimizing the entire sequence of interactions, the whole trajectory, as they call it.
Trajectory, like the whole story of the interaction. Exactly. Imagine the agent sees its state, it thinks about what to do, and they actually encourage that thinking step. Then it takes actions, and then it gets some reward or feedback. StarPO analyzes that entire narrative.
Not just snapshots.
Not just snapshots. It's about the whole flow.
Okay. And to actually try the StarPO idea out, they built a system called RAGEN, R-A-G-E-N.
Mm-hmm. You can think of RAGEN as their test bed, their sort of virtual lab where they could train LLMs using StarPO and really study how reasoning develops during this RL training in these more complex step-by-step worlds.
And the worlds they used, they weren't super complex real-world things at first, were they?
No, and that was actually quite clever. They used simple stylized games, Bandit, Sokoban, and Frozen Lake.
Ah, okay. Familiar names if you're into this stuff.
Right. They might seem basic, but they're designed very specifically to isolate fundamental learning problems without depending on all the knowledge the LLM already has from its pre-training.
Gotcha. So, stripping it back to basics, what did each game test?
Bandit.
Bandit is about decision-making under uncertainty. Think of it like choosing between slot machine arms, maybe labeled Dragon and Phoenix in their setup, trying to figure out which one pays out better, dealing with risk.
Okay, weighing probabilities. And Sokoban, the box-pushing puzzle.
That one brings in multi-step planning. You have to think ahead because one wrong push can mess everything up permanently. It's deterministic, but requires foresight.
Irreversible actions. Tricky.
Yeah.
And Frozen Lake.
Frozen Lake adds probability to the mix. You're navigating a grid. Some parts are icy, so you might slip. Your intended move doesn't always happen. It tests planning when outcomes are uncertain.
Okay, so uncertainty, planning, and chance. They covered different core challenges.
Exactly. These controlled environments let them really focus on the learning mechanics in these multi-turn settings. And their first experiments showed something really interesting and maybe a bit worrying.
Oh, was that?
It seems like training agents with RL for these kinds of multi-step tasks, well, it can be pretty unstable.
Unstable how?
Yeah, they found that if you just grab standard RL methods, things like PPO or GRPO, that work okay for simpler single-turn tasks.
What people often use.
And you apply them to these multi-turn games, things often, while they go off the rails, you might see some initial improvement.
Like it's learning at first.
Exactly. But then quite often, the agent's performance just collapses. It suddenly forgets how to do the task.
Wow, collapse. Okay. Did they see differences between methods, like PPO versus GRPO?
They did note that PPO, which uses what's called a critic to estimate the future value of states or actions, kind of like having a sense of long-term consequences.
A bit of foresight built in.
Sort of, yeah. It tended to stay stable for a bit longer than GRPO, which doesn't have that value estimation part.
Interesting. So estimating future values seems pretty important for these longer interactions.
It suggests it's pretty crucial, yeah. Understanding the downstream impact of your choices seems key when you're making a sequence of decisions.
And this instability,
Yeah.
it led them to identify a specific failure mode, right?
What?
Something they call the echo trap.
Yes, the echo trap. That sounds ominous, doesn't it?
It does. What is it?
It's this really fascinating but problematic pattern they observed. The agent might start out trying different ways of thinking, different actions, diverse strategies.
Okay, exploring possibilities.
Right. But as it keeps training, it starts to converge. It settles into these very repetitive, almost rigid patterns of thought and action.
Like getting stuck in a rut.
Exactly. And often without any really solid justification for why it's stuck on that particular pattern.
They had an example from the Bandit task, I think.
They did. It was quite telling. Early on, the agent might generate varied thoughts, like maybe Dragon is good, perhaps Phoenix is better this time, different hypotheses.
Trying to figure it out.
But later in training, after getting caught in this trap, it might just output the exact same reasoning every single time. Something like, my initial intention is to pick Arm Dragon, over and over.
Without any updated evidence or justification.
Pretty much, just echoing itself.
Wow, so it's like it forgets how to explore.
Precisely. It gets locked into repeating strategies, maybe ones that got a small reward early on, even if they aren't actually the best in the long run. It loses that crucial exploration drive.
And just focuses on exploiting this one, possibly shallow pattern it found.
Yeah, it's kind of like overfitting to its own past behavior, getting stuck in a local optimum. It really highlights that tough balance between exploring new things and exploiting what you know works, especially over these long interaction sequences.
Okay, so this echo trap is a major hurdle. If your agent gets stuck like this, are there any warning signs? Can you see it coming before performance completely tanks?
Yes, and that's a really useful contribution of this work. They identified several metrics that can act as sort of early warning signals, potential indicators that the echo trap might be setting in and performance could drop soon.
Like canaries in the coal mine for AI training.
Kind of, yeah. One is the reward standard deviation.
Standard deviation of the rewards it gets.
Exactly. If you see that number start to drop significantly.
Meaning the rewards are becoming very similar each time.
Right. It suggests the outcomes the agent is getting are becoming less varied. It's likely not trying a diverse enough range of actions anymore. It's settling into a narrow band of behavior.
Okay, so less variety in outcomes is a red flag. What else?
Another one is output entropy. Entropy, in this sense, measures how unpredictable or diverse the agent's policy is, how many different actions or thoughts it's likely to produce.
So high entropy means lots of possibilities. Low entropy means it's becoming predictable.
Exactly. So if you see a sharp decrease in output entropy, yeah, it suggests the agent is becoming too certain, too deterministic in its actions and reasoning. It's exploring less, narrowing its options too much.
So shrinking variety in outputs is another warning. They also mentioned looking at gradients, didn't they?
They did. They looked at the gradient norm. This basically measures the size of the updates being made to the model during training.
How much the model's brain is changing with each learning step.
Sort of, yeah. If you see big spikes in the gradient norm, it often indicates instability. Small bits of new data are causing huge, potentially disruptive shifts in the model.
Like the learning process is becoming jumpy and erratic.
Exactly. It's often a sign that things are getting unstable under the hood, and a performance collapse might be just around the corner.
And the really useful thing is these indicators often started to fluctuate before the average reward, the main performance metric, actually dropped.
That's what they found, yeah. So they could potentially give you a crucial heads up, a warning that trouble is brewing before the agent actually starts failing the task.
That's incredibly valuable for anyone trying to train these things.
Absolutely. And having these early warnings then spurred them on to develop a more stable version of their framework, StarPO-S.
The S is for stabilized, I assume.
You got it. StarPO-S incorporates a few key changes specifically designed to combat these instabilities they'd found.
Okay, so how did they stabilize StarPO? What did they change in StarPO-S?
One of the really interesting changes is what they call uncertainty-based trajectory filtering.
Filtering the training data based on uncertainty.
Mm-hmm. The core idea is to train the agent more on the task examples, where its own results, the rewards it gets, are more varied or uncertain.
So focus on the tricky parts where it's not consistently winning or losing.
Exactly. The thinking is that these uncertain situations where the agent is still kind of figuring things out are actually the most valuable for learning. They contain the most information.
That's counterintuitive almost. You mean they focus on the successes?
Right. But it makes sense. If the agent already knows what to do or consistently fails in the same way, maybe there's less to learn there compared to situations where the outcome is up in the air.
So how did they actually do the filtering?
They figured out a way to measure this uncertainty for a whole interaction sequence, looking at how much the rewards varied across tries on the same starting point. Then during training, they'd rank these starting situations by uncertainty and only keep, say, the top 25%.
Just the most uncertain quarter.
Yeah, they found around 25% retention often worked well, though it might need tuning. And they saw that actually removing those more predictable low variance trajectories really helped. It delayed or sometimes even completely prevented that performance collapse.
Wow. Okay, so filtering for uncertainty is one key. What else did they add to StarPO-S?
They also brought in a couple of tweaks inspired by recent RL research. One was removing the KL divergence term that's usually in PPO.
The KL term. That's the thing that tries to keep the new policy close to the old one, right? Kind of prevents drastic changes.
Exactly. It acts like a constraint, keeping the learning somewhat conservative. By removing it, they're essentially taking off the training wheels a bit.
Encouraging more exploration. Letting it try more different things.
Precisely. Giving it more freedom to find potentially better, but maybe very different strategies.
Okay. So filtering for uncertainty, removing KL for more exploration, and there was a third change.
Yes. The third was using asymmetric clipping.
Asymmetric clipping. What does that involve?
So, in standard PPO, this clipping mechanism limits how much the policy can change based on whether an action led to a better or worse outcome than expected. It limits both the upside and downside adjustments.
Okay. Keeps updates within a certain range.
Right. With asymmetric clipping, they essentially allowed for larger updates when the agent got unexpectedly high rewards.
So learn more aggressively from the really good outcomes.
Kind of like giving it bonus points for big wins, yeah. It lets the policy shift more strongly based on positive surprises compared to negative ones.
Got it. So StarPO-S, focus on uncertain data, encourage exploration, learn more from successes. And did it work? Did it stabilize things?
It did. The results showed StarPO-S significantly outperformed the original StarPO across those three test environments: Bandit, Sokoban, Frozen Lake. It handled the instability much better.
That's a solid improvement.
Definitely. It showed these modifications really targeted those instability issues, but they didn't just stop at the algorithm. They also looked really closely at the data the agent learns from.
Ah, the rollouts. The agent's own generated experiences.
Exactly. If the agent is learning from its own trials, the quality and nature of those trials are obviously super important.
Makes sense. What makes for good training data in this context? What did they find?
They highlighted three main factors. First was task diversity.
Meaning using lots of different starting situations.
Yes, using a wide variety of initial prompts or game setups. They found that giving the model exposure to many different decision contexts while still doing a reasonable number of attempts per setup to learn something.
Not just one try per setup.
Right, you need some comparison. But broad exposure led to better generalization, meaning the agent could perform well on new situations it hadn't seen during training.
So breadth of experience is better than just depth in a few narrow areas.
Seems that way, yeah. The second factor was interaction granularity.
Granularity. How fine-grained the interaction is.
Sort of. They measured it by the action budget, basically. How many actions the agent could take in one go or one turn.
Ah, like how many moves it gets before the environment responds.
Exactly. They found a sweet spot. Around 5 or 6 actions per turn in their experiments seemed to let the agent plan effectively without just making random moves or getting overwhelmed.
Too few actions, it can't plan.
Yeah,
Too many, it's just noise.
that's the idea, finding that right balance for the complexity of the task.
Okay. Diversity, granularity. What was the third factor for good rollouts?
Rollout frequency. How often you update the model with new data generated by the current version of the agent.
Ah, using fresh experiences.
Yes. They found that updating more frequently, using the latest rollouts, led to faster learning and better generalization. The data is more relevant because it reflects what the agent currently knows and how it currently behaves.
Like learning from today's notes instead of last month's.
Good analogy, yeah. Keep the training data fresh and aligned with the agent's current policy.
Okay, so diverse tasks, right number of actions per turn, and frequent updates with fresh data. Key ingredients for good self-generated training data. Now, one of the really intriguing parts, I thought, was when they investigated whether these agents were actually learning to reason or just finding clever ways to succeed without really thinking.
Yes, that's a critical question, isn't it? Are they just pattern matching, or is there some deeper understanding developing?
What did they find there? Did prompting for reasoning help? They use those think tokens, right?
They did. They specifically prompted the agents to output their reasoning before their action. And in the simpler single-turn Bandit task, especially when they made it harder by reversing the usual reward associations.
Like making the good symbol suddenly bad.
Exactly. In those cases, prompting for reasoning actually did seem to help significantly. The agents that had to articulate a thought process performed better.
Okay, so in that simpler setting, thinking seemed beneficial. What about the multi-turn tasks? Sokoban, Frozen Lake.
That's where it got more surprising. In those complex, multi-step environments, the advantage of that explicit reasoning often faded away. Sometimes it didn't provide much benefit at all.
Really? So making it think out loud didn't help as much.
In some cases, they even found that removing the reasoning prompts led to similar or even slightly better performance on the task itself.
Huh. Why would that be?
Well, their hypothesis, and it seems plausible, is that in these complex tasks, the reward signal is just too sparse and delayed.
Meaning you only find out if you succeeded way at the end of a long sequence.
Exactly. And the reward is usually just about the final outcome. Did you solve the puzzle? Did you reach the goal? It doesn't give specific feedback on whether your intermediate reasoning steps were good or bad.
So the agent has no way to connect its internal thinking steps to the final success or failure.
Where the agent's think output seemed to say one thing, but the environment state or the actual outcome suggested something totally different was happening. A disconnect.
Wow. So the reasoning wasn't always grounded in reality.
It seems not always. They did try experimenting with things like format-based penalties, penalizing the agent, if it didn't produce a proper think-then-action structure as a way to encourage more interpretable reasoning, but it highlights a real challenge.
So the big takeaway there seems to be, just rewarding task success isn't necessarily enough to make agents learn robust, reliable reasoning, especially in complex, multi-step problems.
That seems to be the case. You might need more clever reward mechanisms, maybe rewards that specifically evaluate the quality of the reasoning itself, not just the final outcome.
Which is a whole other research challenge, I imagine.
Absolutely. This work really shines a light on how hard it is to train agents that don't just perform well, but also develop the kind of understandable, trustworthy reasoning we'd want in more autonomous systems.
This has been fascinating. A really deep look at the nuts and bolts of training these evolving agents. Just to quickly recap the highlights for you listening. Training LLM agents in these interactive multi-turn settings is tricky. It brings up stability issues, like that echo trap where agents get stuck in repetitive loops.
Right, and the StarPO-S framework they proposed offers a way forward, focusing on learning from uncertainty, boosting exploration, and handling rewards differently to improve stability.
And we saw how crucial the quality of the agent's own training data is, needing task diversity, the right interaction granularity, and frequent updates with fresh rollouts.
And finally, that really interesting finding that just getting the right answer in complex tasks doesn't guarantee the agent is learning to reason effectively. We might need more direct ways to guide that reasoning process.
So connecting this back, this research really points towards making AI agents more autonomous, more capable of learning on their own in complex situations, doesn't it?
It definitely pushes in that direction. Now, the researchers themselves point out limitations scaling this to even bigger models, applying it where rewards aren't easy to define or measure, handling super long interactions. These are still open questions.
Of course. Always more work to do.
Always. But their findings open doors for future work. Maybe agents using different kinds of inputs, more efficient training methods, tackling tasks with really complex goals that can still be checked somehow.
So, as you're thinking about all this, consider the broader picture. What does it mean if we have AI agents that can genuinely learn and adapt through experience out in the world? What possibilities open up? What new challenges arise?
Yeah, and maybe reflect on that echo trap idea, that tendency to get stuck in repetitive, maybe suboptimal patterns, losing the drive to explore. Could that happen in other AI systems?
Or even perhaps in how we learn sometimes. It's definitely something to chew on.
It really is. Yeah. As we build these increasingly capable AI systems, how do we make sure their self-evolution, their learning process, stays aligned with what we actually want them to achieve? How do we prevent them from getting stuck in their own potential limited feedback loops? It's a huge question for the future.